Do not write this down. You will get a copy of this very soon. I didn't get a chance to photocopy it. I had to run out at lunch, and I was on cafeteria duty there last period. But this is exactly what the province of Manitoba says I need to teach you. This is the test outline. I'm giving it to you now, beforehand. It's up on Schoology. You can read it there. What we will likely do is we will likely add to it. This is sort of big picture kind of thing. Identify the four fundamental forces of nature. Perform an experiment to demonstrate Newton's second law. We'll do that. Define the unit of force as the Newton. Well, that's pretty easy to do. You just say the unit of force is the Newton. Done. There you go. Check. Define as the vector sum of all forces acting on a body. Make sure what that means. Define as the vector sum of all. I'm missing something there.
Does this unit involve grams?
Not as much, no. Include the force of friction, normal force, gravitational force, and applied force. We're going to be looking at forces in motion. Construct free body diagrams to determine the net force for objects in various situations. Include balanced and unbalanced forces, and inclined planes, which are fancy words for ramps. Solve problems using Newton's second law and the kinematic equations from last unit. So all those formulas you had last unit, move on over to the next one. And I add one more. Okay? Include forces applied along a straight line and perpendicular forces. So that's sort of the general framework. We're going to sort of expand on that a little bit. You will get a copy of that in the very near future. Today, let's talk about fundamental forces. I highly recommend that you do not write this down. As you can see, the outcome is identify them. In other words, I need to spend about 10 or 15 minutes sort of talking about them for a while. You jot down some important points, and then we'll move on. Okay? Sound good? Okay, I hate when this one. All right, fundamental forces. Let's put the fun back in fundamental forces. Oh, I've been waiting all day to say that. Okay, there are count them, four fundamental forces in nature. Number one, gravitational. Do you want to write down that gravity is the first one? Yeah, that's probably a good idea. When I said don't write it down, what I mean is don't write every single word I'm putting down up there.
All good.
Okay, thanks. Okay, so gravitational force is an attractive force that exists between all objects. Right? We're all sort of attracted to each other in a gravitational sense. How much is that attractive force? Not very strong at all. As you can see, Joey is able to keep himself a small distance away from Jacob. Right? Yes. Okay. So, the gravitational force between the center of the Earth and objects near it causes objects to fall toward the surface of the Earth, right? Now, this is always I always think of this little story. My son, some of you guys know him, he's here at the high school now, and I'm going to make fun of him right now, but when he was real little, he said to me, Dad, how come people in Australia don't fall off the Earth? So I went into a big long thing about gravity, and he went, yeah. But it's kind of interesting when you think that, yeah, there's someone standing down there, right? Upside down, to us anyways, right? Not falling off. How come? Gravity, exactly. So there's a gravitational force. Now, how big is that gravitational force between the Earth and someone in Australia? Considerably larger. It's keeping us all on the floor right now, right? Okay. Good? Number two, electromagnetic force is the second fundamental force of nature. It holds matter together by providing the force that binds atoms into molecules. I'll pick on Ryan this time because he did volunteer earlier. Ryan's atoms are being held together by an electromagnetic force. Keeps him together, so to speak. Maybe sometimes it doesn't work so well.
Sometimes they fail.
Yeah. Okay, so the electromagnetic force is what holds matter together. That's about all you really need to get at that. For example, the force between particles of opposite charge is attractive. It's a nice looking force. Right? We know that from years gone by. The force between particles of the same charge is, repulsive. Disgusting. Right? Terrible. Terrible stuff. So now, think about, this is atoms, right, into molecules. Now, in a single atom, like let's say, who's got their periodic table memorized? Okay, well, yeah, Jordan? Atomic number for, we'll make you an easy one, oxygen. Jake?
8.
I think you're correct. I think it's 8. Which means, how many protons in the nucleus, Jake?
8.
It means 8. Exactly. It says right here, the force between particles of the same charge is repulsive. Are not protons all positive? They are indeed. The force between all those protons in the center is repulsive, and they're trying to be pushed apart. What holds those together, Mr. Bennett? No, neutrons have no charge. No, the electromagnetic force only holds the positives and negatives together. It's what holds the atom together. Holds the electrons whizzing around on the outside in there together with the protons. What's holding those positive ones together? Because clearly, this force would be causing them to repel. Well, there is a third fundamental force. Here it is here. Since like charges repel one another, how can positively charged protons exist closely packed in an atomic nucleus? The answer is something called the strong nuclear force. Now, you can likely presume, based on its name, that it's very strong. Where does it occur? In the nucleus, hence the name. It's what holds protons and neutrons together in atomic nuclei. It is the strongest force of those four. It only acts over very short distances inside the nucleus, extremely tiny distances. So far we got gravity, electromagnetic, and nuclear. By the way, when I'm done with the fourth one, I'm going to ask you to rank them from strongest to weakest, so be thinking about that. I'm going to put all these notes up online as well, so you don't have to. If you want to, get them down later, you can, because I really do need to get on to the next part as well. The last one is what we call the weak nuclear force. It's responsible for some kinds of radioactive decay, such as the decay that creates radon gas, that some of you may have in your basement, by the way. We should really be checking that. I got to remember to do that this winter.
What's in our basement?
Radon gas. It's actually the second leading cause of lung cancer. And
That's because of the indoor furnaces, right?
it's quite prevalent in Manitoba, yes. It has to do with the nature of our soil and the fact that we do have that furnace running and creating a sort of a seal inside the house. It is the next to weakest force and acts only when particles are close together. Okay? All you really need to know is the names, maybe kind of what they do, and how strong they are. So if I asked you to rank them from strong to weak, we know that which one is strongest?
Strong nuclear force.
Strong nuclear force. Which one of the four, this says next to weakest, right? Next to weakest, so that would have to be in this spot over here. Weak nuclear force. So we're left with gravity and electromagnetic. Which one is weaker?
Electromagnetic.
Got some unison over here, and I heard gravity over here.
Ours is in unison, so.
So it must be true. Well, let's think about it logically. If I hold a piece of a pen like this, right? Is gravity pulling it down?
Yes.
Is the pen staying together?
Yes.
Like if I hang on real tight at the top, right? Is the pen staying together?
Yes.
Of course it is. So which one's weaker? Gravity. I mean, I'm stronger than gravity.
Oh, wow. I think we were
And
right.
I'm pretty weak.
We were right.
No, you had it backwards, actually. So which one is the weakest? Gravity. Which one is in here? Electromagnetic. All right. You've been exposed to these. You know their names. You know their strengths. I've covered outcome number one. Hooray for me. I'll post this all up online for you, okay? Because I really want to get into the fun stuff. And this isn't fun. All right, so in grade 10, you were instructed in, or you were exposed to Newton's laws. It was sort of in a qualitative sense in that we didn't really do a lot of formula stuff, or weren't supposed to. We're going to expand on that a little bit. Today is really just a review of everything you learned in grade 10. And if you learned it incorrectly, then hopefully I can fix that. Okay, so dynamics, Newton laws. I heard someone say, "Yeah, look at that hair. That's good hair." Yeah, it was. He'd be right in there in the '80s bands, in the hair bands era, right? I think so. Yeah, that's a weird. You mean the '80s guys or this guy? Yeah, this guy. Okay, so what is a force? A force is a physical quantity that can affect the motion of an object. It's a vector quantity. Why is it a vector quantity? It has magnitude and has direction. Okay, so yes, unfortunately, you have not left the grasps of vectors. You're going to have to deal with them for another unit. Okay. Isaac Newton there, Sir Isaac Newton, was the first person to clearly describe the relationship between force, mass, and motion. So he was sort of the first guy to really sort of do some motion studies. I think he actually was born the day that the same year that Galileo died, I think. Am I right? Newton's laws of motion not only apply on Earth, but they are true throughout the universe, so we call them universal. Do you need to know that? No, just throwing some information there. Anything up there that you really need to write down? No. I don't think so. Okay, these are some different common types of forces. Do not write these down. Okay? These are I'm just going to explain a little bit here. These are not fundamental. When I say fundamental, what does that word mean? What does fundamental mean? Basic, and in fact, every other force could be derived or made up or is because of one of those. These are just common everyday ones that are made up of the fundamental forces. Does that make sense? Okay. So the first one, buoyant force, if you've ever gone swimming or boating, produced by fluids, it acts upward. The elastic force is produced by stretching, compressing, or twisting an object. Maybe stretching a bow or compressing a spring. Electrical force produced by the interaction between charged particles, kind of like, when your socks stick together, come out of the dryer. Oh, you guys probably aren't familiar with the washing dryer, are you? Just the dryer? Frictional force produced when one surface moves over another, acts in a direction always resisting motion. If you were to write something down that was important, it would be that. But that'll come out again eventually, right? Friction is always opposite the intent of motion. Even if there is no motion, there could be friction. Gravitational force, which is actually one of the fundamental ones, is produced by the attraction of any two objects. It acts downward on Earth, or what we think of as downward. And magnetic force is produced by interaction of at least one magnet and another object. Are there more forces out there? Absolutely. Okay, these are just some common ones that you're going to see in problems, I guess is what I'm trying to say. Okay. Newton's first law of motion. You will likely have an idea of what this means already. I'm going to hopefully add on to that. So, and there's many ways to say it. If there's no force acting on a body, it will continue in its state of rest, or will continue moving along a straight line with uniform speed. If you want to write that down, that's fine. I'm going to talk about this slide for a little bit. Okay? You probably know Newton's law of motion as an object in motion stays in motion, an object at rest stays at rest. Okay? This is also known as the law of inertia. If there is no force, in fact, I should probably even adjust this, if there is no net force. What does net force mean, do you think? Total. Yeah, exactly, Jake. Total force. If there's no net force, or if the net force is zero, it will continue in its state of rest, or will continue moving along, and this is important, a straight line with uniform speed. And what does uniform speed mean? Constant. You've seen the tablecloth trick? Okay, so yes, you've seen the tablecloth trick. I got a little other device there, but I think this is just as good. An object at rest will stay at rest. An object in motion, though, will stay in motion. Okay, wise guys and gals. You think you know. Hello. Don't show the answer key. Don't do that.
Show it.
Start assessment. Okay. So I need you to answer yes or no. Is this object moving? We have a box
Yeah.
50 newtons to the right, 50 newtons to the left. The question is this object
I think
moving?
it's a trick question as well, but.
Yeah? I'm not a trick question kind of guy. Didn't I say it just the other day? I'm not in the business of tricking people. I need one more person. Riley? Probably.
This one's broken.
Well,
See, it's a trick question.
everybody said no except for one, but the answer is...
Yeah, it's a trick question.
Ooh.
So is that yes or no?
It's neither.
Okay.
The correct answer is...
No.
Oh, that's right. Trick question, right. But the correct answer is, it depends on what it was doing before, because... Yeah, I know. Hey, it's not about getting the right answer, it's about understanding. No, it's not, you guys. Stop thinking about the right answer.
That's when you marks.
There's no marks here.
Right answer would be 100.
Listen carefully. Don't get all fired up about that. Listen carefully. It depends on whether it was moving before, because if it was moving before, it's going to continue on a straight line at uniform speed. What's the net force? Zero. An object in motion will stay in motion. If it was at rest, it will stay at rest. Now, this is a very important question. I will ask you that question for marks later. I will disguise it. I will not ask that exact question. I'm going to ask that question probably about 10 more times this unit. And the basic answer is always, it depends. Okay? Yes. If the answer is yes, it was moving before, then it will continue moving. If the answer is no, well, then it stays put. Make sure you get that. Newton's second law of motion says, the effect of an applied force is to cause the body to accelerate in the direction of the force. That's kind of high-level thinking, high-level language. The effect of an applied force is to cause the body to accelerate in the direction of the force. In other words, if there's a force, then the acceleration is in the same direction. The acceleration is in direct proportion to the force and in inverse proportion to the mass of the body. I see people writing, so I'm going to pause there for a second. The question is, what's that funny looking symbol in here? This says that the acceleration, no, it's really the proportionality symbol. It looks like that when you hand draw it. Okay? A is proportional to F, and A is inversely proportional to M. If you were just writing it with the M, you would write A is proportional to 1 over M. What the heck does that mean? This is what it means. It means, in other words, the more force, the more acceleration, the less acceleration, the same amount of acceleration, or there's no relationship at all between force and acceleration. And the answer is not, depending on what it was doing before. The correct answer is A. That is exactly what this means. That's what this means.
What? I think this red force is mass.
The acceleration is in direct proportion to the force. In other words, the more force, the greater the acceleration. If I throw a tennis ball and someone hits it with a bat, if they hit it with a large amount of force, it accelerates. If you hit it with a little wee bit of force, it does not accelerate. Right? The more force, the more acceleration. That's important. I thought that would just be sort of intuitive.
I misread it as mass.
There you go.
The more mass, the More acceleration, less acceleration, same amount of acceleration, or once again, no relationship. Sometimes I feel like I'm on a game show when I do this.
There's asking for you. Yeah. After everyone's answered, then you ask.
Okay. Yeah. Well, when you do press submit, it does lock you for answers.
You can.
Yeah.
There you go.
Correct answer is B. The more mass, the less the acceleration. If I push on my filing cabinet and it's empty, it will accelerate. If I push on my filing cabinet with the same amount of force, but it's full, it will not accelerate as much, right? It's an inverse proportion. Inverse. The bigger the mass, right? Like if I have a 10 on the bottom or 100, which one of these has a bigger mass? The 100. Which one of those is a bigger number? 1 over 10 is a bigger number. Right? That's an inverse proportion. Bigger number on the bottom means smaller number altogether. That's what an inverse proportion is. Okay, now, a sort of a corollary or an addendum or an additional part to this law is that if a force applied to a body at rest, the body will begin to move. I.e., if I have a box on a table and I push it, it will accelerate, right? It will accelerate that way. If a body is moving in a straight line and a force is applied in the direction of motion, the body will accelerate. That's really kind of the same as that one, but what they're saying there is that the blue box is already moving, and then I apply a force to it, then what does it do? It's going to accelerate in the same direction. And the third one is that the force applied in a direction not in line with the motion, the acceleration will be in the direction of the force. In other words, if the blue box is traveling to the right, but I decide to push it this way, which way is the acceleration? That way. And which way does the blue box go? Goes like that, right? More on that in the future.
I think that was more than 1 point.
Now, here's a little math for you. Reworking our proportion statement, I'm just going to do some covering up here just to keep you focused. If we rework our proportional statement, you will get the equation. If you take A is proportional to F over M, if I multiply both sides by M, right, the M's cancel and I'm left with MA is proportional to F. Or, if you wish, F is proportional to MA. Now that looks suspiciously like the formula F equals MA. You probably don't know this, but this is what actual scientists do, is they work out relationships like this, and then they have to come up with a number, usually in here, a number that we call a constant, usually called the constant of proportionality. Allow me to give you an example. The area of a circle is proportional to the square of the radius. You don't need to write this down. As the radius of a circle gets bigger, what happens to the area of the circle? It gets bigger. But is the formula area equals r squared? No, you say it's not, Mr. Bennett. What's the area of a circle, Riley? Pi r squared, exactly. Area of a circle is pi r squared. What's pi? It's a constant of proportionality. It's the number that makes it work. Okay? It's the number that makes it work. A lot of relationships have that number, except F equals MA. It does not have that number. Do we have any control over the units of circles? Like, what's the radius of circles measured in? Centimeters or meters or feet or whatever, right? But the area would always be like, if the radius is centimeters, then the area would be square centimeters, right? Okay, but here we've got units, mass, kilograms. Units for acceleration are meters per second squared. So when you take mass times acceleration, you have kilograms times meters per second squared. Now that's kind of a weird unit. Kilogram meters per second squared. It's hard to say, it's hard to write, it doesn't make a lot of sense. golly gee, wouldn't it be nice if we had a unit that was equal to a kilogram meter per second squared that we could just substitute?
Yes.
Let's honor someone famous like Newton, and let's define 1 Newton to be, because a Newton doesn't really exist except in our brains, right? We combine the units for mass and acceleration, and we come up with the unit for force, kilogram meters per second squared, and we define that as 1 Newton. So the constant of proportionality, when I plug it in here, is actually, it's actually 1. Right? Just as pi is in here, because we can control this, we define what a Newton is, we put the number 1 in. Could we have used 10? Sure. We could have said that 10 newtons is equal to 1 kilogram meter per second squared, but that would be stupid. Why would you want to do that? Why not make it 1 to 1? So that's what they did. Okay? They made it 1 to 1. Now, I ask you this. If I had a unit named after me, what would it be measuring?
Bad jokes.
I'll allow you to enter your answer
Oh my gosh, what?
if you want. You can go to polev.com/CABennett. I'll check the answers at the end of today's lesson. You can also text this number and your message to that number there. I'll leave that up there for about 30 seconds if you want. All right. Last law of motion. Newton's third law says, when one body exerts a force on another, the second body exerts on the first a force of equal magnitude in the opposite direction. Why would I highlight equal and opposite, do you think?
It's like
Huh?
So they're not going to spend.
Equal and opposite, excuse me, equal and opposite are pretty important. That's why I've highlighted it. When one body exerts a force on another, the second exerts on the first a force of equal magnitude in the opposite direction. Now you've probably heard it explained like this. For every action force there is a reaction force. And some people might say an equal and opposite reaction force, right? Equal and opposite is important. When one body exerts a force on another, the second body exerts on the first a force of equal magnitude in the opposite direction. If I come up and I drill Anderson in the head, not going to do that. But if I did that with, say, 1,000 newtons, pop them one, how much force on my fist? 1,000 newtons. It would in fact hurt me as much as it hurt you, wouldn't it?
Yes.
Right? If I push on the desk here with, say, 100 newtons, is the desk pushing back on me?
Yeah.
How much?
100 newtons.
How come I don't move?
Because it's equal.
Ah, the old it's equal thing. If I push on the desk with 100 newtons, how come that desk doesn't move? I'm pushing on it with 100 newtons.
Hold it to the ground.
Ah, it's bolted to the ground. In fact, it's friction that's holding it in place. So if I push on here with 100 newtons, friction holds it in place. It pushes back on me with 100 newtons. What's holding me in place? Friction. Right? I got shoes on. They're not that, they're kind of slippery, but if I was on ice and I was wearing curling shoes and I pushed on the edge, I would go backward, exactly, and crack my head and be off for another 6 months. Okay. This occurs at all time in nature. This is happening everywhere, 100% of the time. Almost. There is always an action force and a reaction force. Example, a book lying on the table exerts a force on the table, and the table exerts an identical force on the book, except for one small thing. Opposite direction. Is it not? Opposite direction. Equal and opposite. All right, my friends, have you been listening? The correct answer is 50. Did I try to trick you? Absolutely I did.
You said you're not trickster.
Well, I know, but it'd be way too easy if I didn't try to trick you a bit, right? This 50 Newton weight is what? 50 newtons. It's a It's a what?
Force.
Force. So the force down is 50 newtons, which means the force up is 50 newtons.
So why did you choose gravity
To trick you. To see if you were paying attention.
And the only reason it's on the table and not going upward is because of gravity.
Well, okay.
Yes, that's equal.
Ryan says if there was no gravity, would the book go
No,
up?
it would stay in the same place because it's equal.
But there's no gravity, there'd be no force down. But if there was no force down, there would be
No force up.
no force up.
Still the same. Until it gets pushed.
There has to be something to exist on the one side for there to be the opposite. Okay? There has to be that equal and opposite. The table feels the downward push of your hand. What do you feel? You would feel the, what do you think the teacher's looking for here?
Upward push.
The upward push of the table. Now, believe it or not, I've had students that will refuse. They argue with me up and down. If you push down, they did not believe that the table was pushing up.
Yeah.
What have I been talking about for the last 20 minutes? If I push down, the table pushes up, doesn't it?
Just
Well, the
stays there.
reason that
Well, of course it stays there. What's the net force?
You can't push it through the ground, so it's not going to happen.
And there's yeah, exactly. I'm not going to push it to the ground. Allow me to demonstrate another way. Did I lose my volleyball? I had a volleyball. Did I lose it?
you lost it.
It's too bad, 'cause it was good for this. If I push down on the table with the tennis ball, try to find a place where you can see, does the tennis ball flatten out?
Yeah.
Why does the tennis ball flatten out? Because the table's pushing on it.
Pushing it.
No, I'm not pushing on it. The table's pushing on it. I'm pushing on the top.
So if you put your hand there, it just automatically pushed up.
I pushed on the top. The top flattened off.
If you said you didn't push on it.
I'm not pushing on the bottom of it. I'm not touching the bottom of that ball. I'm touching the top. I push on the ball pushes on the table, and the table
Push on the ball.
pushes back.
Maybe the ball's so conscious, try to suck it.
Oh my god.